Okay, so hey everybody. Today we're going through Vakil's The Rising Sea, starting at page 10, 1.2.3, localization of rings and modules. And I'm hoping to get us maybe through like fiber products and co-products. Um, if it's a really good day, we'll get through Yonita's lemma and up to limits and colimits, but I'm not gonna like put a strict bound on that. Um, okay. So yeah, when we talk about universal, the kind of the point of this chapter of Vakil is to talk about universal properties of certain categories, and of certain diagrams. And so we're talking about localization of rings, first as basically a universal property that we want to pull out of a specific example. Um, So basically, starting with the localization of a ring, we're going to define a I can never spell this the first time. Multiplicative. There we go. A multiplicative subset S of a ring A is a subset which is closed under multiplication and contains 1. And so then we're going to define the inverse multiplicative subset of the ring, which is the localization at S, is basically the set of A over S such that A is in A and S is in S. So it works kind of exactly as we would like it to. And so we have a canonical mapping. Canonical map from a ring A into S inverse A, given by A getting sent to A over 1. So this is an injection. Notably, A is a subset of its field of fractions. So if you take A to be a subset of itself, then A inverse A is basically the Cartesian product of A or the set of A over B such that A, B are in A. This is weird. We don't usually write it like this. Okay. Now, there are two particularly important flavors of multiplicative subsets. The first is basically, so I guess let me give this a section heading. Two flavors. The first is of the form 1f, f squared, and so on, where f is in A. And so then the localization, I'm going to call this, yeah. Well, we'll just leave it as is. Its localization is denoted by a subscript f. And basically what this is it is 1f f squared dot 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 inverse A. So it's just 1 over f, or f to some power of A. And this is kind of the case that I'm going to lovingly call the one where we can divide. Where we can divide. But the second case is where division is maybe not well defined. And so if you have maybe like an ideal. And so the second is A set minus P, where P is a prime ideal, meaning it's generated by irreducible polynomials of the ring. By irreducible polynomials over A. And so basically, its localization Dr. Scott. Hey, Dr. Scott.
Yeah, sorry about that.
No worries. But the localization by this prime ideal P is denoted by A subscript P is kind of the opposite of what we would think. AP means you're allowed to divide by elements not in P. Is A divided by elements not in P. And so then the ideal, like the localization of the ideal generated by a polynomial is not the localization of the polynomial, right? So if P is generated by F, the confusing point here is that A localized at F is not the same thing as A localized at the ideal generated by F. So in this one, we're dividing by powers of F, and in this one, we're dividing by things not in the ideal generated by F. It can be a little difficult to keep track of this. So yeah. Any questions on this or on notation or something like that?
I think I'm good.
Oh yeah, I see Miriam typing, so I'm just waiting for her. Can I give an example? Yes, I can absolutely give an example. Okay, let's consider Z localized, or I guess let's do, yeah, no, Z actually works. Z localized by 2. And so this is this is not Z2, by the way, just being very clear. This is not Z mod 2. We'll denote Z mod 2 from now on by Z quotient 2Z, or maybe GF2. But yeah, so Z localized at 2 is the set of like minus 2 over 2. And I guess really it becomes like Q, but powers of 2. So like 1 over dot dot dot. 1 over minus 1 over 4 minus 1 over 2. 1 1 over 2 1 over 4 times Z. And so we could just as easily pick one of these things and list out, something isomorphic to Z and get like, minus 1/2, 0, 1/2, 1, 3/2, and so on. But we could do that for any of these, right? So like if we pick minus 1 over 4, we get minus 1 over 4. Or I guess that would be positive 1 over 4 if we start with minus 1. Then going to 0, we get 0. 1 over 4 is minus 1 over 4. Minus 1 half, minus 3/4, and so on. So that's an example of like the localization at 2. Alternatively, the ideal generated by 2, so z localized at the ideal generated by 2 is all of the things which are, you can divide by all odd things. So anything that is not a multiple of 2. So we can divide, notably, not by 1. We can divide by like 3, 5, 7, 9. Yeah, I think just any odd number will work. So we'll just say z divided by odd integers, but not 1. So does that make sense? Cool. Okay. Any other questions about localizations of rings?
I have an answer, more of like an ontological question that I've been trying to think about. And I wanted to ask you, why are quotients so important in ring theory?
Yeah, so, and that's a good question to ask, probably for the whole class. So a quotient is basically taking an equivalence class of something that like partitions the ring, right? So like it lets you project down into something that like is intrinsically connected to the ring by something that defines an equivalence class. So there's like a general theorem that says that equivalence classes partition sets. Um, and so you can think of a quotient really as just like an inclusion map into the partition of the set. So like in topology, the idea of the quotient topology is saying, you can identify partitions of open sets with like A, B, C, D, E. And so any like you can get a continuous function to the quotient topology because the open sets in the quotient topology are just like A, B, C, D, E, singleton sets. And then their inverse images are the things in the partition. Um, Equivalently, like you can think of quotients as like if we partition up, if this is our set S, then it can be a group, a topology, whatever. And maybe we have like A, B, C, D, E. This could be a very non-finite group or ring or field or topology or anything, but we can identify this open subset in blue with A. And then we can identify this open subset with B. And then this open subset with C. And so it really actually, like, it has a lot more to do with the equivalence class that we use to partition the set that maybe tells us something about the underlying structure. Or alternatively, if we know that like the quotient of the set is like, in this case, if we define an additive structure where A moves to B, B moves to C, C moves to D, D moves to E, then this is maybe isomorphic to like the additive group of integers mod 5, right? So Z mod 5. And so like you can say, oh, well then the quotient under this equivalence class is modular of order 5. It also motivates stuff like finite fields. That's very important for computing. So there's like the idea that a field of order p to the n, where p is prime, is perfect, meaning that you can define polynomials with coefficients in it, and all of the roots of those polynomials will be contained in that field. And so that actually kind of like motivates the structure of most classical computing architecture. And that all comes from Z quotient p to the n z. And that's GF p to the n.
Makes sense. Thank you, because I was reading something about cryptography that is related to just what you said. So thank you.
Yep. Yeah, and so in cryptography, they typically like using these perfect fields of characteristic p or otherwise, because you can define things and do faster arithmetic on it. So there's this thing that you might be interested in looking up after the lecture called Polya's fast addition. And it's literally how to use modular arithmetic to make addition slightly faster in low-level programming systems. I was fascinated by it for a little bit. There's another way that you can do it with like elliptic curves as well. That actually it takes longer, but it's like a weird way of doing addition, basically, that comes out of quotient structure.
Yeah, I was reading about I was reading about elliptic curves and how they're efficient algorithms that they use, the basis for efficient algorithms for cryptography. So yeah, I'm it's clear. Thanks a lot. I appreciate the explanation.
Yeah, that's actually so elliptic curves are a big focus in arithmetic algebraic geometry in the last 30 years. And they're really interesting to me for a lot of reasons, but it's a lot of algebraic geometry has come out of the theory of elliptic curves. And that's something I want to kind of take us into. I would love to work through like Fermat's last theorem eventually. Like once we get through more of Vakil, maybe like the first 12 chapters. Andrew Wiles did his proof of Fermat's last theorem, and there's a copy of it that somebody used as like a lecture resource that he typed up in LaTeX and published in 2003. So I've been reading through it on my own, and I'd like to kind of steer our seminar in that direction of, oh, let's do Fermat, because it involves this stuff called Galois cohomology, which is a numerical invariant that tells us some stuff. And so basically that comes into the proof of Fermat's last theorem, but that deals with elliptic curves. And so there's a lot of applications of elliptic curves from arithmetic algebraic geometry in classical computing. So anyway, I know that's probably a long tangent for like Miriam and Garrett here, but yeah, elliptic curves are cool, and quotient stuff is important. So I'm going to present a theorem, and this is presented as an exercise in Vakil. And so I asked Garrett earlier to go through and prove this for homework. But basically, the theorem is that if A is a ring, the inclusion defined here, the canonical ring map, is injective if and only if S is if S has no zero divisors. And so,
Tim, can I check my proof real quick?
yeah, go ahead and run it by me.
I said, because it's got to be two ways. So the first way, I assumed that it was injective. And since it was injective, kernel of phi, I just defined eta as negative 1 of A as phi. I said curve phi had to be equal to 0.
Yeah.
So, so A over 1 had to be equal to 0 over 1, like because curve phi of A over
Yeah.
1 had to be 0. So that meant A was 0. And if A was 0, uh, well, for S to be a zero divider, we needed S times A to be 0 when A was not equal to 0. And A meaning 0 was a contradiction. So that proved that
Yeah.
one way around. And then the other way, I said we had no zero divisors. Said S times A had to equaling 0 meant that A had to be 0. So then,
Not that what I'm not quite with you on.
okay.
So let's just say let f of x1 equal f of x2 um, equals 0 in not in A, but in S inverse of A. then, and by f, I'm just letting f be the map here. Well then, we want to show that it's injective, so we want to show that x1 is equal to x2. And A has no zero divisors. And so the only way that like x1 could be not equal to x2 is if S inverse of A has zero divisors. And so we can either assume for contradiction that S inverse of A has zero divisors, and then we can backtrack it and we can say, okay, well, if these two things are equal, maybe they're both equal to zero, but maybe they're different things, and we get something in A where x1 is not equal to x2. Or we say, okay, S inverse of A has no zero divisors, do it constructively, show, okay, x1 is equal to x2, because otherwise we would get a different image. So does anybody want me to write that whole thing down, or does saying it like work for people?
You mind writing it down?
Yeah, let's do it. So let's do it both ways, actually. So the constructive proof is that, okay, so S inverse of A has no zero divisors, and then f of x1 we'll just say is equal to A over B, and f of x2 is equal to C over D. So then A over B is equal to C over D implies that dA is equal to BC is equal to 0. And so then this means that either A or B, or sorry, A or C, respectively, both have to be 0. But then f of 0 equals f of 0. Right? Implies 0 equals 0 in A. Does that make sense?
Yeah.
And then, do you want me to do the by contradiction way?
I'm all right.
Okay. If nobody else wants me to, then we can move on. Yeah. There's kind of like a proposition that Vakil throws in here. So A and A is a non-zero divisor for M if and only if the Cartesian product with A from M to M is injective, or in the language of commutative diagrams, if we have some zero element going to M by XA is exact. Don't need to worry about this yet. We will talk about exact sequences soon enough. And then we'll probably come back here. So kind of as a notation thing, and this is really for Garrett because I don't think anybody else has been following along in the Hartshorn series. So if A is an integral domain and S is equal to A set minus 0, then S inverse A is the fraction field of A, and Vakil calls it K of A, which is what we use for function field in Hartshorn. Now, they're connected because the function field is the equivalence class of open subsets and regular functions on those subsets. But they're very different things. So when Vakil says K of A, he means function field. Or sorry, fraction field, not function field. But yeah.
All right, sounds good.
Yeah, this one is a category theory proof. Yeah. Okay. I'm just going to post this as a theorem, but I'm not going to spend too much time on it, so maybe I won't prove it. So A inverse, no, A to S inverse A, is universally initial among A algebras. B, where every element of S is sent to an invertible element in B. And so an A algebra is basically a well-behaved vector space. And well-behaved vector spaces have this nice property of multiplicative inverses. And so basically, like, this just makes sense. Universally initial means that S inverse A, sorry. S inverse A is universally initial. S inverse A has a mapping to every A algebra. So any A algebra that you can make, S inverse A for the specific A, like, gets sent there. And just as an example, consider S is equal to Z minus the zero set. Then S inverse Z goes to any Z vector space. So does this make sense? Okay. Yeah. And so the clear way of defining this by a universal property. So as a diagram, let M be an A module and let phi from M to S inverse M be initial among A module maps from M to N such that elements of S are invertible. N, notably, N is also an A module, pretty sure. And so basically the diagrammatic construction of this is that M goes to S inverse M by phi, which goes down to N and this factors uniquely, meaning that any alpha factors uniquely through S inverse. And then phi is unique up to unique isomorphism. So, does this make sense? Okay. I know category theory is new to everybody here, so it's totally okay to ask questions and for us to get stuck on tangents. We've been going really quickly, and like if we were to do one page for a 2-hour session, that would still actually be pretty good time, given that I mean Garrett's a sophomore, I'm a junior. I'm not sure what year Miriam is. Dr.
I'm
Scott.
also a sophomore, yeah.
Yeah, so like I think even if we were to spend like the full 2 hours doing one page, if we really understood the one page, I think that's the victory. So this is at this point very much a guided reading plan, and so nobody left behind. Okay. So if nobody has any questions about this commutative diagram or the way that we've expressed this, I'll go ahead and move on to the next thing. Yeah. Oh, I guess so. The next thing is that phi exists. Right, because we can always take S to be the trivial group. So if nothing else exists, then the trivial ring is just 1. And so then we can send M to S inverse, and it works out that it's just M to M to N. Now, there's like a chain of propositions here. So proposition 1 is that localization commutes with finite products and direct sums. And so basically what this means is that if we have like a product I equals 1 to n of maybe AIs localized at and the whole thing is localized at f, or equivalently the ideal generated by f, this is the same thing as the direct product I equals 1 to n of AI localized at f, or the ideal generated by f. So when we say it commutes, this is kind of what we mean. As like a computational example, we can say that like just kind of using our thing, maybe like Z2 cross Z3 cross, let's pick something larger. Z7 cross Z3 cross Z11 localized at 2 is equal to Z7 localized at 2 cross Z3 localized at 2 cross Z11 localized at 2. And I'm just going to denote that these mean mod, and this means localized, and this means mod, and this means localized. And I know that this is terribly obfuscated notation, but bear with me. Is this clear to everybody what I mean when I say localization commutes with finite products and direct sums?
Yeah.
Okay. Miriam and Dr. Scott, is this working notations clear? Okay, cool. So then our second proposition in this chain is that localization commutes with arbitrary direct sums. And so this is kind of the same meaning, except that arbitrary can mean some indexing set I. So for I and I, which may be countable or uncountable, right? So like the real numbers are uncountable. Q is a countable set. Both are infinite. So these AIs localized at F, or the ideal generated by F, is equal to the direct sum I and I of AI localized at F, or the ideal generated by F. You might be thinking, what's the difference between a direct sum and a direct product? That's a very good question, because I'm kind of thinking that right now. I've always seen them used interchangeably, except in linear algebra. So like the direct sum of matrices is like this, whereas the direct product of matrices is like this, I think. But I'm not sure what that means categorically. So let me Google that real quick and give you an answer. Difference between direct sum and direct product. So the direct sum only exists for abelian groups. It looks like. The direct sum is specified by injection maps of inclusion. These maps have a universal property that any other group with maps will factor through these. The direct product is projection maps. For finite groups, they're the same. An element of a direct sum of infinitely many groups can only have finitely many entries. Yeah. Direct sum notation is more natural for abelian groups. What is nice about the direct sum of abelian groups GI? Yeah. I see. Okay, so then basically, and I'll just add this as a note. What I'm seeing online is that direct sums are characterized by injection, whereas direct products are characterized by projection. So basically, theoretically, like the direct product of a bunch of abelian groups, like if you take any group on its own, categorically speaking, like Z5 really should be written as Z5 direct product the trivial group. Because it's a projection down from the category of groups. Direct sums are characterized by injection, and so we actually can just get rid of that pesky like direct product trivial group. So basically direct products have like the minimum number of things, and everything is like non-trivial. Direct products, you would include like the trivial thing. And that really only matters for like these for these non-finite examples. And then localization. So the third proposition is localization doesn't necessarily commute with infinite products. And so basically the way that this happens is that S inverse times the product of I and I of A modules to the product of I and I S inverse MI. Isn't strictly an isomorphism. And the hint that they give is that 1/2, 1/3, 1/4, ... and Q cross Q cross So I guess what they're saying here is that this is really Z set minus 0 inverse Z cross ... versus Z set minus 0 Z is not an isomorphism because it doesn't admit a unique inverse. So you have a left inverse and a right inverse that are not the same. It is a bijection, I think, but it is not necessarily like an isomorphism. Is this making sense to people? Okay. Okay. So now we get to kind of the meat of today's lecture, which is tensor products. So of the three of you, have any of you three worked with tensor products before? I will go first. I have not.
I've seen them in physics, but I haven't worked with them extensively.
Yeah. I'm kind of in the boat of like I've seen people use them in like engineering classes, and I've always kind of been like, I mean, I use the direct product symbol. That's as close as I've gotten. But yeah, we have one calculus professor at our school who him and his wife both teach tensor products in their Calc 3 class. And I always felt kind of gypped. I had a great Calc 3 professor who I love very much, but I always felt kind of gypped that the one thing we didn't cover was tensor products. So I guess now's the time to learn. Yeah. So of A modules. So the way he defines it is the tensor product of A modules is the object. Wow, I just combined three words. Normally you get the thing when you're talking, it's like you'll combine two words at once. I just combined three. That's got to be like an achievement. Okay. The objects of the category of A modules. Sent to the objects of the category of A modules by the map to A modules M and N get sent to M, A tensor product N. And really, the elements of the tensor product M and N are elements defined by M cross N such that M is in M, N is in N, and arithmetic is subject to M1 plus M2 tensor product N is equal to M1 tensor product N plus M2 tensor product N on the right. And I think we get bilinearity because they're A modules, so it doesn't really matter, I think. 2M times N1 plus N2 distributes the way we want it to. I guess it's tensor product N1 plus M tensor product N2. And then A times M tensor product N is equal to AM tensor product N is equal to M tensor product AN, where A is in the A module, M1, M2, or sorry, A is a scalar, M1 and M2. For each of these. And so then, as a remark, if A is a field, whoa. Okay, if A is a field, we recover the tensor product of vector spaces. And this is the one that I guess shows up in physics. We're kind of going to use tensor products in a way that nobody in applied math does, as far as I know. Maybe in some machine learning papers. I really don't know. I don't know a lot about machine learning. But I'm sure I've seen some people use tensor products. But yeah, so as an example, we want to show that Z quotient, the ideal generated by 10, tensor producted by Z quotient, the ideal generated by 12, is isomorphic to Z quotient, the ideal generated by 2. Well, so we know that we're sending things to basically things. And is it? I guess it is the quotient. C quotient, the ideal generated by. I'm trying to figure out if they mean. I'm just looking up notation real fact. real fact real quick. There we go. Okay, so it does mean Z12Z. So this is Z mod 10. This is, I guess, how Vakil denotes mod. That's a really weird way of doing it. Okay, whatever. That's fine. So then we have basically this notion of if we have a few things, I guess we probably want to run through definitions 1 through 3. So let's pick, let's do this color in orange and this color in blue and run through these definitions. So M1 plus M2. So like, I don't know, let's do 3 mod 10 plus 5 mod 10. Tensor product something mod 12. Let's do like 7 mod 12. Well, this should be equal to, I guess, 3 times 7. And then, I guess, how do you determine what the mod is? I guess this is the crux of it. Let me look it up. I mean, it seems Z tensor product. Yeah. Oh, okay. So it's Z mod GCD of AB. That's how it's defined. So the way that they get the mod 2 piece is that this has to be the way that the Z tensor product is defined, so that this is mod GCD of 10 and 12. That's the missing piece of information here. So then this is plus 5 times 7 mod GCD 10, 12, which is equal to 21 mod 2, which is 1, I guess congruent to, plus 35 mod 2 is also 1, is congruent to 0. Yeah. So yeah. The way that we form this is that basically trying to find like the general way to compute the Z tensor product. So if we start with the Cartesian product and then we mod out by the distributive subgroup. Oh, that sucks. Okay, so he had a line in here in the definition that I totally skipped over because I was like, that looks horrible and unnecessary. It's not. So there's this really long expression. I guess there's a submodule generated by oh my god, I don't want to have to write all of this. m1 plus m2 comma n minus m1 comma n minus m2 comma n, and then the second generator is m comma n1 plus n2 minus m comma n1 minus m comma n2, and then a times mn minus amn. Wait, that's, yeah, amn. And then the final generator is amnn. That doesn't look like an A here. Minus m comma an. And this is a submodule of any of our A module this is a submodule of m cross n as a Cartesian product. And if we quotient m cross n by this submodule, then we get the tensor space. And for z, this happens to be defined by the GCD. Which that just sucks. So let me just see if this is the same thing for any A module. Because A modules have Euclidean division algorithms, so I'm assuming it's just the GCD. Like, it would be awesome if for any ring A, we can get that A module, like tensor products of A modules are generated by the GCD. So is any tensor n, I guess tensor of A module a quotient of m times n mod GCD of characteristic of m characteristic of n. Oh, but then you get infinite modules. Oh, that's why you have to have the other thing. So, okay, so if both m and n are cyclic, then, so I guess I'm going to call this constructing tensor spaces. So if m and n are finite A modules, then we're going to no, the GCD formula is a special case. That's only for Z modules. Ah, I hate that. So it just has to be, yeah, I mean, if M and N are A modules, then the thing that we end up using is we're just going to call this submodule Y. M over N quotient Y is M A tensor product N. That's just terrible. Ugh. Why? Why would anybody do that? Yeah, so in the special case of Z10, Z12 being isomorphic to Z2, and I guess this is an isomorphism, then yeah. I guess let's compute what the submodule looks like. I don't know how to do that in a particularly efficient way. um, hmm. Is this making sense to you guys at least?
A little bit.
Kind of, yeah, kind of.
Okay. So in the special case, of Z modules, which are finite abelian groups, in the special case of Z modules, then basically Z product N is isomorphic to basically Z mod GCD characteristic of characteristic of N. And so the way that like we would construct this is like it just comes down to the division algorithm for basically seeing if this submodule is like generating stuff. That sucks. That's so tedious. How the heck did people ever use these for something useful? Okay. I'm gonna move on from this for now because there are just properties of tensor products that we use categorically. And I'm assuming that we can just look stuff up about tensor products as we need to use them. There aren't enough exercises here that like are just making sense. So the next exercise in Vakil has to do with these things called exact sequences. He talks about them in like 10 pages. So we're just going to come back to this in 10 pages because otherwise it's just really confusing. Oh, this is nice. So he's talking about tensor products. Just kind of like as a remark. He says, the constructive definition of the tensor product, the way we've done it here, is a weird definition and really the wrong definition. To motivate a better one, notice that there is a natural A bilinear map from M cross N to M tensor product N, and that any bilinear A bilinear map M product N to P factors through the tensor product uniquely. And so then the definition of the tensor product, the way it categorically makes sense, is that it's an A module T along with an A bilinear map from M cross N to T, such that any A bilinear map factors uniquely from T to T prime. Okay, that makes a lot more sense to me. I'm going to write this down, and I think it will help you guys too. At least for how we're going to use tensors, because I don't know. If I find myself in a research area where I'm computing a ton of tensors, I might go crazy. So here's hoping. I have one friend who's an engineer who I did a research project with like a year and a half ago. And I caught up with him the other day for like 20 minutes. And apparently he's really big into tensor calculus now. And I have no clue how one would go about even doing that. He's an engineer too, so it's really impressive like that he's going so far in on it. He does like geometric algebra, which is not the same thing as algebraic geometry, by the way. This is totally a tangent thing. Geometric algebra is like basically the math behind computing where robot arms go. and like computing frames of reference for different hinges of like robot arms. And so it's basically the notion of the wedge product being like the exterior product of a manifold. So you have like kind of adding things in orthogonal directions. That's geometric algebra. But he does a lot of that now. So anyway, that just made me think of it. Okay, so a better way of seeing the tensor product. So the tensor product is an A module T along with an A bilinear map. So, okay. Is an A module along with an A bilinear map, meaning that it distributes from both sides, like the distributive property holds from both sides, plus the other weird rules of the tensor product. A bilinear map, lowercase t prime from M cross N to T such that given any A bilinear map, T prime from M cross N into T prime, there exists a unique A linear map, not bilinear map, but a linear map F from T to T prime such that T prime is equal to the composition of F and T. And the commutative diagram for this, I think, is the part that makes sense, not that definition. That definition still sucks. But M cross N going to T, which is really the tensor product of M and N, by T factors uniquely through F to the A module T prime. So this is like the intuition for it. So we send any product, M product N, factoring uniquely through the tensor product by this A linear map, which is not a bilinear map. So the thing that is the tensor product is this A module T along with the bilinear map T prime. So this is a linear, and these two components are the tensor product. So T and T prime little are the tensor product categorically. Yeah. If I had to title this lecture, I would probably call it something along the lines of localizations, tensors, and co-limits oh my, or something like that. I don't know. My girlfriend is watching the new Wicked movie in theaters right now, and she keeps texting me updates, and so my brain is in a wicked mood. Um, okay. Any questions on this construction?
The last part seen, I saw that from quantum mechanics. So that last diagram is familiar to me. Um,
Really? This
yeah,
shows up in the QM textbook.
yeah. Like I think when you're dealing with disparate states which are linked, they're linked through the tensor product. So I just saw that, I remember it and just vaguely, and then I just looked it up and I said, yeah, it's familiar. It looked familiar. So um just given what you were saying, is something that I've always, I guess, wanted to ask, like the mathematicians. Um, like for instance, when I learned linear algebra, a lot of it was guided by physics. Um, Problems in physics. I'm not saying it was developed by that, but the way that it was taught was guided by physics. And I guess one of the things that I wanted to ask, what guides like mathematicians in developing the math in the way that they do? Because I'm trying to see a pattern in what they write down. Like for instance, when I try to look at what Sophie Lee did with algebra, I don't see a pattern as to what's leading him. So I've always wanted to ask a mathematician, what the hell is leading you? There's no model, there's nothing. It's none of that. And I'm just trying to, I'm not trying to, I don't mean it derogatory, but I don't understand what, like. And also one of the things which I guess is odd, to me, they start off with, make, they create these definitions, which, and then they run through these manipulations, and then at the end, they have this beautiful theorem. It's like, you created the definition. Did you know that it was going to lead to this? I just like,
So
but yeah. So I'm just, yeah.
this is really funny because I had this exact conversation at dinner before this seminar with my dad, who's an economist, and my grandfather, who's a historian, but whose brother studied physics at Caltech. And so my great uncle studied under Feynman at Caltech back in the day, and so my grandfather was like exposed to like the physics of physics
Oh
at
my
family
God.
dinners and stuff. And so both of them were kind of asking me, what the hell is it that you do? Because the seminar before this one that I gave, we proved that basically wallpapers have no fivefold symmetry. Um, and so they asked me what I was doing, and I said that, and they said kind of your same question of like, first of all, what the hell made you think like to go from point A to point B and like set up stuff to get there? Two, like, what's the motivation of caring about that in the first place, besides the fact that it's generally interesting? And then three, just kind of like, what the hell? Um, I will phrase this in the way kind of that I learned linear algebra, because that I think is really the best example. So algebra is a beautiful subject because you can approach it immediately out of like a high school education. With like university calculus, you're handed calculus as calculus does this. Don't worry about why it works. Algebra is something that like you've grown up doing the rules and computations of, and that to do calculus, you're familiar with, and so it's very pure in the way of it's constructive. Calculus, obviously on some levels constructed, but very few people take analysis, and people who do oftentimes lose sight of like, why are we constructing this? Um, Linear algebra, especially for mathematicians, came out of a few things, none of which were really application focused, but ended up being very useful for applications. Um, which really is just that it is an interesting way of describing certain types of varieties, like as an algebraic geometer or like an aspiring one at least. Um, you think about like the kernel as a subspace of a vector space, like the kernel of a linear transformation. And so everything, or like the image of a linear transformation, it all becomes centered not around the application, but around the structure. I think a lot of math research and a lot of like quote unquote new math that gets developed just comes from people tinkering around with like ideas. For example, the research that I do, that my research grant is for with Dr. Field at JMU, we're working on this thing that's basically just making a new notation for this thing called the Brouhaha order that just sucks. It's very difficult to compute. It's very time intensive. It's basically going through and making permutations, and we have a way of developing the full post set visually. And so we're working on proving that that notation works. But I mean, to prove it, we've had to prove all of these other weird lemmas and things that just totally didn't fall out of what we thought was going to be the proof for this thing. I mean, you would think it's pretty simple. You have the elements of your partially ordered set under this notation, the elements under this notation. You think you should be able to line them up, but the problem is however infinitely large you get, or close to infinitely large, there's still infinitely many more. So you have to do induction. Well, induction's not so easy. You need a bunch of lemmas. And so literally, I have spent most of break that I haven't been doing teaching making flashcards. There are 96 flashcards here, each of which has 6 computations on them that I have filled out 3 notebooks making. um, and it's not for any other reason than it's just kind of like an interesting puzzle. And to solve one problem, I've had to generate a lot of new math, a lot of which has led absolutely nowhere, but is going to end up in our paper because it's useful for somebody for something. So there are algorithms that we've come across and made for like faster ways of computing certain blocks of the fixed point free group of involutions if you append an identity element to it. For like, okay, if you see this grouping of fixed point free involutions together, you know it composes to this permutation. And is anybody ever going to use it? Absolutely not. If anybody ever used it, I would actually almost be offended because, like, there's something nice about knowing that, nobody cares, right? But I don't know. I think a lot of it is just people screw around with the structure of things. A lot of math is just about kind of ascertaining structure, and a lot of applied math is about looking for kind of structural equivalences between things in math and things in the real world. And this is the fundamental thing with like calculating numerical invariance of varieties, like with cohomology. Cohomology is a useful tool for differential equations and came about, like the de Rham cohomology came about to solve differential equations because it computes the vanishings of like smooth manifolds which map to differential equations. And so, you know, in a way, I was kind of thinking about it earlier today. Like the difference between me and a guy who plays professional Tetris is that he probably gets a little bit more recognition for doing it. Um, but there's nothing wrong with that. Like it's kind of the same method of problem solving, just without any particular goal in mind sometimes. Or like sometimes the goal in mind leads to different findings along the way. Sorry, that's like a long-winded way to answer that, and I don't know if it's particularly helpful to the question, but that's been my experience.
It's fun. I just, again, it was just something that I was on my mind given coming to the seminars and trying to understand the patterns in your lectures and what you are striving for. Is just a question I had in my mind. Again, I meant no disrespect.
Oh no, I get it.
Yeah.
I think most mathematicians get this a lot. But I mean, it's a perfectly valid question, and it's not wrong to look for applications of very abstract math. But there are plenty of mathematicians who, like to a lot of them, like my complex analysis professor is one of those people. We were talking about it. And like there was this one guy in our class who was basically he was an engineer and he kept asking questions about basically how is this going to help him land a rocket someday. Um, and basically my professor's answer was it's not, and I would be kind of upset if it did. Not because like it's wrong for you to want to, but like to me it's very beautiful that it doesn't need to have an application for it to be interesting. Um, I think a lot of mathematicians think that way. Um, and it's not to diminish, beauty and application. Like obviously, I'm very interested in national security. I have been for a while. I love the idea that my math could protect U.S. citizens and U.S. armed forces. Um, but also at the same time, there's, a real beauty in the fact that nobody's ever going to use my paper on, a new notation for the Bruja order of fixed point free involutions. If they do, I'll be very happy and very honored. Um, there's kind of the running joke of what do you call someone who reads like a category theory paper, a co-author. I might co-author with them. But like, it's something that like I think it's interesting because it's interesting to me, and I like playing around with it because I've come to enjoy just making flashcards after flashcards and like trying to tie them together in different ways and see how things relate. So anyway, yeah, hopefully that's a helpful answer. So, in the last 40 minutes, I think we can get up to the Unetta lemma. I think we can do that. So the next exercise to really understand this definition is to show that our previous construction of the tensor product, this thing, satisfies the universal properties of tensor products, which is this thing. Um, and so basically, what we have to do is we have to say, okay, well, we have this product that sends M A modules and N A modules to their tensor product with the bilinear map that satisfies 1, 2, and 3. And then that product is this T. And so we want to show that for T prime, where we're sending some bilinear map down to T prime, which is an A module, that this A module, and really like the implied thing here is that this is an isomorphism, that F is an isomorphism. At least in the cases that we care about for like computing things, we want to show that this T prime is an A bilinear map that factors through F. And so I think that the way to do that is to pick something in M cross N, send it through T prime to capital T prime, and then to take that same thing in M cross N, send it through the map T, pass it through the map F, and show that we get the same thing. I don't want to have to do that. I think that's something that everybody can do on their own if I write the steps down. So show that these definitions work. And so the way we're going to do this is let Mn in M Cartesian product M, and maybe let U equal T prime of Mn. And so then show that F circ T prime, or F circ T of M comma N is equal to U. And that's how we would show that our original construction of the tensor product is universal. Any questions on that? Okay. So the next one is called an important. The next three are called an important exercise. So okay. Um, So proposition, if M is an A module, and F from A to B is a morphism of rings, give B tensor product M the structure of a B module, and then show that this describes a functor F from A modules to B modules. And so what we're saying is that we have a morphism of rings between A modules and B modules, and that since we have a morphism, we want to take basically F inverse of B tensor product M and use the universal property to show that it's an A module. Or rather that it's a Cartesian product of A modules. So I think just as a proof sketch, and I want you guys to be kind of critical on this. So we have A to B as a morphism of rings. We have B is a ring tensor producted with M. Well, B tensor producted with M satisfies the universal diagram. T goes to B tensor product A with an A module, which factors as a B module, which we will call B prime. By the universal property of tensors, we get that this factors uniquely, and that T prime is bilinear. And then we want to take this thing as a B module, and we want to say that taking F inverse of B cross M by some other thing, maybe L, to F inverse of B, and this will be where it's error reversing, so we need to put F inverse of B on the right hand side. Is that clear why I'm switching the positions? Is it clear why I just switched the positions of everything? Okay. Yeah, so the whole business of error reversing equivalence. Otherwise it would flow the left-hand way. And then this is going to flow down into an A module. And I guess we shouldn't call this F. We should call this G. And we'll call this H because we're running out of letters. And we'll call this T or L prime. That's what we'll call it. L prime factors here. And then the idea is that we have a functor of objects and a functor of morphisms. And that those things are encapsulated in the same structure of F. So essentially what we're saying is that F of T is equal to L, F of T prime is equal to L prime, F of G is equal to H, F of B Cartesian product M is equal to M Cartesian product F inverse of B, F of B A tensor product of M is equal to M B tensor product of F inverse of B, and then F of B prime is equal to M. And I think that that shows it. So, is everybody satisfied with that? Does that seem like it answers the question?
It works for me.
Okay. So, the next one is tensor product of rings, and it's showing that the tensor product. Wait, what? They do not define. He does not define that. Hold on. That's terrible. Okay. So proposition, and I'm just gonna write it down and see if I can make further sense of it. So if further, I guess this builds on the last one. A to C is a morphism of rings. Show that B, and then what tensor product is used? As an A tensor product with C is a ring. And this gets later reinterpreted as 1.2U. Where? Sorry, I'm crashing out. What the heck? 1.2U. Oh, that makes sense now. Okay, I get it. I get it. Okay. So we're gonna reprove this on the next page with this thing called a fibered coproduct. Yeah. We are not hitting the unit lemma tonight. We'll get there on maybe Monday, I guess. Oh, that's a good reminder. I have to reschedule Monday next week. So Monday of next week I will not be able to meet. I have to proctor an exam, so we'll have to do the rest of this on Wednesday of next week. But okay, so A to C is a morphism of rings. Show that B, which up here is a ring, So B is a ring, C is a ring. The tensor product of two rings is a ring. I feel like I can take that at face value. Tensor product of two rings is a ring. Are we good with that?
Yeah.
Okay. I'm pretty happy to move on from that one. Okay. So now, exercise. There's no way to say this one is a theorem. Oh, there is actually. Okay, never mind. I'm gonna say it's a theorem. Okay. So if S is a multiplicative subset of A and M is an A module, there exists a natural isomorphism, S inverse A tensor product, to S inverse M. And it's an isomorphism of modules, and I'm just gonna call it phi. So this looks like we're gonna have to pull out the the quotient thing. This thing. It looks like we're gonna have to actually compute something. Oh God, I don't want to do that. So the way I read this is that we should compute what this tensor product looks like, or like what. Oh, never mind. I know it. I get it now. Hold on. I'm just gonna fill it in, and it's all gonna make sense. Unless I write my M like that again, in which case it's over. S inverse A, tensor product A, and then S inverse A, Cartesian product. Boom. There exists a unique phi, and then T prime. Boom. Am I cooking or am I cooking? All right, I think that is essentially what we need to show, is that this diagram commutes. Yeah, that's definitely what we need to show, is that this diagram commutes. Proof. This diagram commutes. No, I will not elaborate. No, I mean, we probably should compute it, actually. But yeah, okay, so we just need to throw something in S inverse A cross M. Okay, so I guess this is really a want to show that this commutes. So let A over B cross some vector V in S, this thing. And then we want to say that, well, T prime of A over B Cartesian product V just gets sent to A over B, just because this is an inclusion map. And so what we want to do is we want to show that everything in the tensor space is basically just a copy of S. Oh, it's not A. Oh. It gets sent. Ah, that's it. Okay. Does that make sense? So it's not an inclusion map. It is injective. This is definitely injective. And actually, that has to be a bijection. Oh, and then that's the proof. Okay, that makes sense. Okay, hold on. It's clicking now. Um, so the trick here is that basically these two things are an isomorphism. The way you get to that isomorphism is by saying, okay, well, the injection is clear. Any two things like come from the same thing. The surjection is also clear because any A over BV has a clear like fiber in S inverse A Cartesian product M. And then by universal property of tensors, we just need to say there exists this unique isomorphism phi that T prime factors through. And so we just want to say T prime factors through phi. And I'm just going to say this gives a clear isomorphism, like without even showing anything. We have a very easy way to do and undo this. We have a very easy way to show injectivity and surjectivity. So we just want to show that T prime factors through phi. And then this means that we need to show that T prime factors basically like a... Okay, hold on. What are our criteria? The three criteria for tensor products. This is what we got to compute. So for any M1, M2, and N, like here, we want to show that A plus or A over B plus C over D tensor product V, which is equal to A over B tensor product V plus C over D tensor product V has phi of this thing as a linear map, and then this is the key, is that the tensor product is bilinear. All we need to show is that phi factors linearly. So this factors straight to A over B, vector V plus C over D, vector V, which is equal to V over A over B plus C over D. And so step 1 is done. And then step 2, it literally just goes through computing this stuff. Okay. Is everybody happy with, does everybody understand why this proves the thing that I'm saying that it's proving?
Yeah.
Okay. So let's do this for step 2. We want to say, okay, so A over B times V plus W is equal to A over B tensor product V plus A over B tensor product W. And that works. So phi of this definitely factors to A over B, I guess just times B plus A over B W. And that's definitely in here. Like that's definitely in S inverse M. And so then the third thing that we want is to show this. And so then taking something in the A module, oh, that's where this gets tricky. So it's just AMN. And this is an A tensor product. So it's just A times B over C tensor product V is equal to AB over C tensor product V is equal to B over C tensor product A V, and then this thing has phi of AB over C tensor product V is equal to AB over C V is equal to phi of B over C tensor product AB. There we go. And so then, yeah, now we've shown that T prime factors uniquely through phi. So T prime factors uniquely through phi. So does this proof make sense?
Yeah.
So yeah, we've tied together universal properties of tensors. We've tied together our actual construction of the tensors. And then we've shown that tensor products of A modules with rings give a functor between A modules and B modules. We've shown that tensor products of two rings give a ring. And then now we've shown this thing about localizations of A modules and a natural isomorphism between tensor products. Tensor products commute with arbitrary direct sums. I don't want to prove that. That sucks. I'm just going to state that as a theorem. Okay. Tensor products commute with arbitrary direct sums. And just the way this works is M tensor product I and I is equal to, or is isomorphic to, the direct sum I and I of M tensor product and I. Okay, so I'm going to end this. We have 10 minutes left. I want to get through one definition, just kind of to be thinking about for Wednesday. Two definitions, actually. We're going to do two definitions. One is fibered products. The other one is pullback diagrams. And then that will set you guys up so that you can all do exercises until Wednesday to get up to the Yonetta lemma, and I think we should wait to do that until class together. So, okay. So definition, fibered products. Let alpha from X to Z and beta from Y. I can never write Y's. That's crazy. Y to Z in any category be morphisms. The fibered product is an object x, z, y, along with morphisms. Oh, what the hell? I'm gonna call these pi because they mean projection. Pi x from x fibered product y to x and pi y from x fibered product z. No, x fibered product y to y. There we go. That's the difference. Where the two compositions alpha composed with pi x and beta composed with pi y agree such that W in ob C with maps to x and y factor uniquely through x fibered product y. And this is just the product, except they're pullbacks of z. So like here, the diagram's just gonna make a lot more sense. You've all seen this before when we've talked about products. The key is that we're just going to talk about pullbacks in kind of a special way. So this is pi y. Yeah, pi y. This is pi x. This is alpha. This is beta. W has some map to y and x. And then the key piece of this whole endeavor is some unique factorization through the fibered product. So we usually refer to this thing as the fibered product. And so then as a definition, and this is what I will actually end with, is that oh no, I shouldn't have used pi. Fuck. Okay, we're gonna use what's another p? We're gonna use psi. That works. No, that's just too much notation to change. We're stuck with it. Pi is up there, psi is down here. So if psi from x to y is a morphism, then x fibered product through z of y exists and determines a diagonal morphism delta of psi from x to the fibered product of y with x. And the diagonal morphism is actually kind of the key here. And so basically, x with the fibered product of y getting sent by pi of y to y and then to x and to z is called a we're gonna say like a pullback diagram. Okay, there's like 6 ways you can say this. Fibered slash pullback slash Cartesian, and then either diagram or square. And Vakil actually has a really funny way of putting this. He says, depending on your religion, this diagram is called a fibered slash pullback slash Cartesian diagram slash square. And basically the right way to interpret it is to think about what it means in the category of sets. So anyway, this is kind of like our last definition for the night, because we're about to hit 9. The important thing to note is that the fibered product can also be called the pullback. So this is called the pullback of Z. And we'll talk more about why next time. So I'm just gonna throw out there, Garrett and I are gonna keep meeting at 8 in the morning, not tomorrow because it's Thanksgiving, but Friday, Saturday, Sunday. We're gonna meet 8 to 10 in the
I can't
mornings.
meet on Sunday.
Oh yeah, because mass. And neither can I because also mass. But yeah, okay. So then Friday and Saturday we're gonna meet at 8 to 10 in the morning. And we're probably gonna keep chugging along in this. So I'm gonna record those lectures and I'm gonna post them to YouTube on my YouTube channel that I linked above earlier, where I have the Hartshorn videos. The key thing is, if you can't come to those things, please watch the videos and please send me questions, because I'll give you guys my phone number. I'm gonna give you guys my phone number after the recording ends. Important thing here. But I'll give you guys my phone number after the recording ends. Text me any questions that you have on the lectures if you aren't able to make 8 to 10 EST on Friday or Saturday. Because we will keep moving along and this will keep getting more confusing, I promise.
Morning, you said AM or PM?
AM.
Okay, cool.
Yeah, so Eastern Standard Time, like New York City time.
Okay. And this Saturday and this Friday and Saturday?
Yeah, just this Friday and Saturday. And are you in the US right now?
I am. I'm in Texas, so it'll be 7 a.m. Yeah.
Okay, that'll be 7 a.m. Okay.
But next week I'll be back home, and it'll be a 7-hour time difference, so I'm not sure I'll be able to make it if it's at 9.
Yeah, then we'll keep recording it for you, and you can just send questions as you have them.
Yeah, I've been watching your recordings. Sounds good. Thank you.
Okay, cool. All right, then I'm gonna go ahead and stop the recording, and I will see you all Friday at 8 a.m. Happy Thanksgiving.
I just wanted to say one last comment. I thought this looked familiar. What you're doing is gives you a lot to chomp on. Pullbacks you see in quantum field theory. So I thought I saw it in my book, and I seemed familiar. So a lot of the math, again, I've seen like tastes of it in very, very advanced quantum field theory. So just a side note. Yeah, it is. It's very interesting.
That's if you can send me the reference text, that sounds really cool.
Yeah, it's a lot of the stuff that you're doing is really out there, but it's really interesting. So just a side note. So thank you for taking the time to lecture. Appreciate it.
Yeah, of course. Thank you for listening. All right, I'm gonna go ahead, stop the recording, and yeah, happy Thanksgiving.
Happy Thanksgiving, Tim.